Welcome back to another explainer. Okay, today we're diving into an absolute classic in the world of data structures and algorithms, pulling right from Striver's A to Z DSA course. We are going to break down the logic of the majority element problem step by step, moving from the most basic, kind of panicky approach all the way up to a pretty brilliant topical solution. Here is our roadmap for today. We'll start with the majority element problem itself, then check out the brute force trap, the hashing compromise, Moore's voting algorithm, and finally, the crucial verification step.
All right, let's jump right into Section 1, the majority element problem.
So, what are we actually looking for here? Well, imagine you've got an array of integers, and let's say it's size n. Your mission is to find the element that appears strictly more than n divided by 2 times. To put that into perspective, if your array has 7 items, taking the floor of n over 2 means your target number needs to show up 4 or more times.
Now listen, this is absolutely crucial, and it's where so many candidates trip up. The occurrences have to be strictly greater than n over 2. Hitting exactly half? Nope, not gonna cut it. It's a total trap. Like, if your array is size 6, you need 4 occurrences, not 3. You really gotta keep that strict mathematical distinction in mind as we evaluate our solutions today.
Moving right along to Section 2, the brute force trap.
Picture this. You're at the whiteboard, maybe sweating a little. You're in panic mode, and you go for the most intuitive solution. That's usually a massive scanning operation using nested loops. You pick the very first element, scan the entire rest of the array, and just count it up. If it's not the majority, well, you just move to the second element and do the whole shebang all over again.
Now, the logic there is perfectly sound, sure. But look at the performance table. Your time complexity completely skyrockets to big O of n squared. Now, space complexity stays at O of 1 because, hey, we aren't storing any extra stuff, but trust me, any interviewer seeing that n squared time is immediately going to ask you for an optimization.
Which brings us to Section 3, the hashing compromise.
Okay, so how do we beat n squared? We can actually track frequencies using a hash map. It's kind of like sorting things into buckets. We just iterate once. The array element becomes our key, and its frequency becomes the value. You see a 2? Increment the 2 bucket. See a 3? Increment the 3 bucket. After that, you just check which key clears that n over 2 hurdle. This hashing approach is a real game changer for time complexity. Depending on the map you're using in C++, Java, or Python, traversing and inserting knocks your time right down to around O of n log n. That is a huge win. But hold on, take a look at the space complexity. In the worst-case scenario, where literally every single element in your array is unique, we are storing all of them in our map. Our space complexity just ballooned to big O of n. We traded space to buy speed.
And right on cue, your interviewer leans in, kind of squints, and asks, wait, you're using additional space? Can you optimize this? This is it. This is the ultimate test. They want that lightning-fast execution time, but there is no way they're letting you pay for it with an extra memory tax.
This is where the magic happens. Section 4, Moore's voting algorithm.
Let's walk through exactly how this works on the fly. We're going to track just 2 variables, a count which starts at 0 and an element which starts off empty. We start iterating through the array. Step 1, if our count hits 0, we grab the current array item, crown it as our hypothetical majority element, and set our count to 1. Step 2, as we keep moving, if the next item matches our assumed element, we just increment the count. Step 3, if the next item is different, we decrement the count. Now, this quote right here from the source material absolutely hit the nail on the head for me. If someone appears more than n-2 times, it will not get canceled. Think about that for a second. If an element makes up more than half the array, even if literally every other element gangs up to decrement its count, the true majority mathematically has to outlast them. It's going to be the last one standing when the array ends.
Looking at our final table, Moore's algorithm hits the absolute sweet spot. One single loop brings our time complexity down to a blistering big O of n. And since we're only storing a simple count in an element variable, bam, space complexity shrinks right back down to a perfect O of 1.
So, you've written down Moore's algorithm, the time is optimal, the space is optimal, you are ready to celebrate. But wait, there is a massive hidden trap here. Moore's algorithm operates on a completely blind assumption. It assumes that a valid majority element actually exists in the array. But what if it doesn't? What if literally no element clears that strict n over 2 hurdle?
And that brings us to Section 5, the crucial verification step.
Look, if the problem explicitly guarantees the majority element, you're golden. You are done. But if it says there might be one, well, Moore's algorithm is really just handing you a surviving candidate. To guarantee it's the right answer, you have to manually verify it. It's super simple, though. You just do one final pass through the array. Count exactly how many times your survivor actually appears. If that final true count strictly exceeds n divided by 2, boom, you safely return it. If it doesn't, you just return -1, proving to the interviewer that you handled that edge case flawlessly.
So, to wrap it all up, your complete, foolproof formula is just 2 steps. First, apply Moore's voting algorithm to efficiently cancel out the noise and find the surviving candidate in linear time with 0 extra space. Second, run a quick verification pass just to ensure that candidate is mathematically legitimate.
You know, mastering Moore's voting algorithm isn't just about solving one specific problem. It literally reshapes how you think about space and time trade-offs. It shows why intuition beats memorization every single time. Because honestly, the difference between a good candidate and a great one is knowing not just how an algorithm works, but exactly why it works. So as you gear up for your next whiteboard challenge, ask yourself, what other hidden structural traps are waiting in your next technical interview? And how can you use pure logic to break them down just like we did today? Keep learning, keep optimizing, and we will catch you on the next explainer.